Also, let us take one more example to clarify how the frequency can be found out for the ring counters. Let's take this circuit diagram for the ring counter using D flip-flops, D2, Q2, Q1. This is D0, Q0. So that as per the definition of the ring counters, the output of LSB acts as an input to MSB. This is the clock pulses, and since synchronous, they all have the same clock pulses. Now, in n-bit binary ripple counter, the LSB frequency is always f clock by 2 and MSB frequency is f clock by 2 raised to n. So we can write it down, which is a very important and crucial data for n-bit binary ripple counter. LSB frequency, this is LSB, this is MSB. Okay, LSB frequency is f clock by 2 and MSB frequency is given by f clock by 2 raised to n. Okay, and in case of a ring counter, the frequency of waveform available at the output of each flip-flop is same and equal to f raised to n. But if they are phase shifted with respect to each other, the amount of phase shift between any two consecutive flip-flop output waveform is 360 raised to n. That is, we can also have a phase shift in the output waveform for n-bit flip-flop. For n-bit flip-flop, the amount of phase shift between any two consecutive flip-flop, that is, for example, if there is an n-bit flip-flop, the amount of phase shift between these two consecutive flip-flop is given by 360 by n, is the amount of phase shift for waveform. Shift for waveform. Now let's see the next type of counter, next type of synchronous counter, which is Johnson counter. This Johnson's ring counter has different names, not only one name. It is also called as twisted ring counters, twisted ring counter, or Mobius counter, or creeping counter, walking counter. Why it is called as a twisted ring counter? Let's check it down from its circuit diagram. To see a rough diagram, I'll draw. This is Q2, Q1, Q0. This is Q0 and this is Q0 bar. So the output Q0 goes here and this goes here, and Q0, as we can check out, Q0 comes here and this acts as a twisted, therefore it is called as a twisted ring counter. Now let's see the working of Johnson's counter. Let us assume initial stages be 0, 0, 0. So the working can be calculated like clock input Q2, Q1, Q0 over let us say initial stages are 0, 0, 0. For the first clock pulse, let us say input is 1, so this one goes here, this goes here. How we can say initial stage is 0, 0, 0? Let us say Q0 is initially 0, therefore Q0 bar becomes 1. This one comes as an input to Q2. That is how I have got 1 here. So this 0 becomes 0 and this 0 goes here. Now during second clock pulse, Q0 again becomes 1, which becomes therefore 1, 1, 0. Now during third clock pulse, the same way it becomes 1, 1, this 1 becomes 1. Fourth clock pulse, this Q0 is 1, therefore Q0 bar becomes 0 and this 0 comes here as the input, therefore we get the input as the complement of Q0, which is 0. Fourth is 0, 0, 1, 1. fifth will be 0, this comes here 0, 0, this comes 1, and sixth clock pulse will give 0, 0, 0 and 0. Therefore the above circuit is mod 6 ripple counter, as it repeats at 6 counter. So for n bit Johnson ring counter we can have a mod of 2 raised to n. Therefore let's note down some important and very interesting data about the Johnson ring counter. For n bit ring counter, n bit mod is 2n, and this condition is true only when the initial conditions are 0. So when initial condition should always be 0, that is in this way. So we can check or we can verify this from here. For n bit, for 3 bit we have mod 6, that is for n bit we get mod 2 raised to n ring counters. To maintain the synchronous, for synchronous counter to maintain the sequence, again the condition is very crucial, like how we got for the asynchronous counter. Let us write down a new pad, a very crucial data to maintain the counting sequence of synchronous counter. The condition is T clock should be greater than equal to TPD, where TPD is the propagation delay of each flip-flop, and therefore F clock should be less than equal to 1 upon TPD. To summarize the operations of all the counters, whether it is synchronous counter, asynchronous counter, or different kinds of mod counter, let us take one simple problem of how to calculate the mod and what can be the mod value for different counters. Let us say the block diagram for the circuit is having the input clock frequency as 1 Hz. Let's say input clock frequency is a question 1 megahertz. So the output, determine the output clock frequency. Let's start with one block diagram, which is a 3-bit block diagram, 3-bit Johnson. This is 3-bit Johnson. This is a 3-bit ripple counter, then 3-bit asynchronous counter, mod 13 counter, followed by 3-bit ring counter, followed by 5-bit parallel counters. So what would be the output frequency? Let us start with the 3-bit synchronous 3-bit Johnson counter. Assume the initial condition to be 0. So since the initial condition is 0, therefore the modulus of a 3-bit Johnson counter can be found out. 3-bit Johnson counter can be found out. Therefore modulus is 2n is equal to 2 into 3 is equal to 6. Now 3-bit ripple counter modulus for a ripple counter is 2 raised to n, this 2 raised to 3, 8. Now mod 13, its modulus is given as 13 itself. For this 3-bit ring counter, its modulus is 3. Now the last is 5-bit parallel counter. Therefore by default modulus is 2 raised to 5, which is 32. Now to find the output frequency, we need to find out the modulus, which we have found out, and the output frequency will be the input frequency, your input frequency, which is around 1 megahertz, divided by the multiplication of all the modulus. So we can find out, therefore F output can be found out here. F output is equal to F clock, that is the frequency of clock, upon total modulus, which is F clock upon the total modulus can be found out by multiplication of each stage individually, that is 6 into 8 into 13 into 3 into 2. This is the output frequency of the above circuit diagram, that is the output frequency output is f clock, which is 1 megahertz given in the question, upon 6 into 8 into 13 into 3 into 2. So is the total output frequency of the above circuit given. That is, to find out the output, we had to find out the modulus and divide the total modulus by the input frequency.